So it's not a huge point in this video, except it is something that's coming to State College. If you've never been to see Radical Reels, it's put on by some local outdoor group. It takes place in the State Theater, which is on College Avenue, near Allen Street, I guess. Well, you probably know where it is. And it's on October the 1st. So if you're interested in spending an evening doing something that relates all of these things, many of these things have a fluid mechanics connection, as you can imagine. Certainly surfing West Virginia, kayaking, cycling, wind resistance, balance between wind resistance and power. Many of these, obviously, in this case. So anyway, so we'll just get our excitement going before we delve into what we'll do today. Any questions from last time? That's a negatory.
Welcome to the Banff Mountain Film Festival Radical Reels Tour.
You should think about the questions that you'll do for your presentation. I will.
All right, so you know what's going to happen, right?
The best questions to do, I think, are ones that are kind of unusual, aren't obvious as to what they are. This one is, why do, when you shake up a can and open it, why does it foam out? Not so fluid mechanics-ish, more thermo in some respects, because it involves dissolution and exsolution. And it's still, so if this one comes up, we can, we'll sit. So why does a can explode when you shake it up? Didn't really want that.
Okay, so take your key.
I don't want to overprint mine. So something that's kind of a little, has some curiosity attached to it. Not everyone knows the answer, or you have to work out the answer. Someone sent me a video over the weekend of water trapped between the glass of a bus, an accelerating bus, talking about waves last time and how to explain exactly the motion you had in there. I think that would make a fine presentation as well. Perhaps that person gets first dibs on it. So this is talking about how, when you tap the side of a can before you open it after you've shaken it, why it doesn't explode. It's because you dislodge all the bubbles which are on the walls. They go up to the headspace, and then it doesn't explode on you. I'm sure you can think of all kinds of others on the juvenile, bordering on the juvenile. Of course, you can't bring any drinks into the class. But, of course, one question is why, if you have a bottle...
Go. Nope.
Well, you see it, right?
Start chugging up. No, don't you let that shit pop out. Nope.
So why is it when you tap a bottle on the top with another bottle, when you're standing around with your buddies, why does it foam? What's the reason for that? What's the mechanics of that? Any thoughts? I think it's all to do with waves that we talked about last time. But so I'll let you figure that one out. Maybe we'll talk about that at the end of the class. Yeah. So you can't bring any beer to class, but of course you could do. I think you could do that example by doing a couple of cans to see if it works. You could do it with a soft plastic bottle to see if it works. I think it's, when you tap it, there's an acoustic wave, a seismic wave goes down the side of the bottle, hits the bottom, reflects as a tensile wave, cavitates the beer in the bottom, sends it into gas because it's less than atmospheric pressure, and it pops out the bottle. So you could test that, because I think you need a really sturdy glass wall to be able to carry that acoustic wave. If it's really soft, like a soft plastic, which you could do, put a fizzy drink in a soft plastic and try it. If it doesn't work, you'd have part of, maybe that at least zones in on the hypothesis that you have. So that's bringing us up to kind of where we are. So we're 4 minutes in. What else do we have to talk about? Any questions on procedural stuff? Nothing? Great. Good to see a sea of faces still with us. Today we'll move on from talking about fluid properties to try and use those fluid properties in some way, as we mentioned last time. And the desire is to be able to talk about magnitudes of fluid pressure. And and how those change with location. And so I tried to gather some things that look at this and why we might be interested in this. I can think of a number of reasons for this. This is a 60 minutes piece. Actually, I think it played this weekend or two weekends ago on free diving. So the idea is that you take a breath and then you dive down as far as you can and then come back up. And people go down amazingly. I think it's, I don't know if it's 100 meters or 300 meters, but it's an incredible distance. And so I won't go through this, but you can imagine that to be able to figure out what the pressures are at depth, you'd like to know that. One reason is if you're working as a diver and you're breathing nitrogen from an air tank, you only have a certain amount of time down there before you come up. If you come up and you don't go into a pressurization chamber, if you've been working deep, the nitrogen that's come out of the air into your blood comes out of solution and puts bubbles in your circulatory system, which is not a good thing, right? Your heart gets occluded by an air bubble, can't pump blood anymore, and you die. It's called the bends, as many of you know. And so knowing what the depths are and how long you can stay down at those depths is an important issue. In oil and gas, we talked about, this probably isn't the best one to use, but we talked about the Macondo well incident. I don't know if this is going to work. You know, the BP disaster of 3 years ago, when you drill a well, you don't want gas to blow out the top. So one of the things you do is that you fill the well with drilling mud, and the drilling mud balances the pressure of the fluid at the bottom. So you have to know what the fluid pressure bottom is and how that column of mud weights down
Drilling
that
fluids
fluid
are
so it
used to
doesn't blow out
perform the
well.
following 6 functions. To stabilize the well bore while controlling subsurface pressure. To suspend drilled particles and transport them to the surface.
And so drilling mud you use for a couple of reasons, actually. You don't want the hole to collapse on you. So you have the fluid in the well bore that's pushing out on the walls so the walls don't collapse. And so you have this column of liquid which is denser than water typically because it has solids added to it. And it keeps the sides from caving in. But it also stops the fluids, typically a gas cap that you might have in it, pushing out the well and blowing out to the surface, which of course in the Macondo well it didn't do. And of course when you complete a well, you have casing down that's inside the larger borehole, and you want to cement that casing in. So you put concrete down or slurry of concrete down, you blow it down to displace it up between the casing and the hole, and then you want it to solidify there. And that's exactly the problem that in the Macondo well didn't happen, and there was an air gap or a gas gap between them which allowed the gas to migrate up to the top of the well. So again, we want to know what the pressure change is with time to be able to figure out what the mud weight might be to be able to apply to that. And so I'm going to get rid of these because I think they're a bit heavy on the bandwidth. And for other things such as Malpass Dam. Malpass Dam was a dam that failed when I was 1 year old and when you weren't born yet. But it was built in the south of France. It was an arch dam, a very thin structure. You can see a picture of the remains of it here. This is the arch that remains. It used to span all the way across this valley. It was built on a bad foundation. There were faults in the foundation that moved. In moving, it destroyed the dam, and as a result of that, as is the case with many dams, the big hazard with dams is that if it breaks and you live downstream, you get wet. And people got more than wet. It killed 400 people as it rushed downstream. And this was just well, I guess you know how old I am now. This is just a simulation of the dam break. I don't know if it's going to come up in time. Let's see if it does. It's thinking, I guess, right? And this wave of water runs downstream, and it wipes away all the people in front of it. So, as you can imagine, you can simulate these kinds of things. It's a bit more sophisticated than anything we'll do in this class, but this is just the idea of a model that allows you to look at this bead of water, if you like, but it's not a bead of water anymore. It's running over a DEM model of the surface of the former riverbed, which was excluded from flow by the fact that you had a dam upstream. So you'd like to know what the fluid pressures are at a point and how you go down with depth behind the dam, because that integrated profile of pressure with depth gives you the force that's applied on that dam. And the force that's applied on that dam is what's resisted by the abutments. And if you don't design it properly, then problem. And so all of these things, again, that are things that speak maybe to the issue of our responsibilities of engineers and scientists to be able to deal with these issues. Okay, so that's perhaps motivation for it. So I'm going to kill these so that they, so long as that, I just don't want them overplaying my sonorous voice, competing for space on the recording that goes on these. Has anyone looked at these YouTubes, by the way? You know where they are. I've had some subscribers. You can subscribe so you'll see the new ones come up every time if you so wish. It's up to you. But anyway, all right. So where are we? Well, I guess this is a bit further. So what we'll do today is we'll do what we normally do. We've talked a little bit about why we might want to do this. The easiest way to introduce this is to maybe talk about how we calculate the fundamental relationship that we're going to end up with today is going to be this. And it says how pressure changes with depth. We could also write it as an ordinary differential, as the question was last time, because it only varies in one quantity, which is pressure only varies with z, which is our vertical direction, remember, from our right-handed rule. And but it's not the same as, for instance, we'll use substantial derivative. It's not the same as this. So often in the things that we do, partial derivative and ordinary derivative will be similar to each other. This is somewhat different, and we don't have to think about that for now, but we'll deal with that in due course. Okay, so let's look first of all at pressures at a point and how they might change. I guess I can use it on, I'll do this. So do I want to do full screen? All right. So where are we? We are period 2 perhaps. So we're interested in how fluid pressure varies with depth. So here's our thought exercise. So let's take our coordinate system and write how we expect fluid pressure, not rho, but P for pressure, changing with depth. And let's think about a can of fluid, liquid, actually not fluid. Well, it could be, fluid. Could be fluid, could be a closed can. And the fact that that can, if it's weightless and was filled with something, would have some weight attached to it. And so what we're going to do is we're going to look at how we might plot that change in fluid pressure changing with elevation. So this is positive z direction, remember? This is our negative z direction, you said, right? From the right-hand rule, is always do this. And so what we can do is we can get the weight of that can is going to be equal to what? It's going to be the density times gravity. So this is density, not pressure, times gravity, times the volume of the can. And if we give this can an area and a length, let's call it Z1, then the volume clearly is just going to be the cross-sectional area multiplied by Z1, right? So we can write this as density times gravity times area times depth. If we want to know what the fluid pressure is acting at this point, how do we define fluid pressure? We define fluid pressure as equal to the weight of the can, which is only really the fluid, divided by the area. And if we substitute this term in here, we get, not surprisingly, we get rid of this and this. We have density times G times Z1. This is the weight due to 1. And we can also write that, as you know, as unit weight. So unit weight is just the product of density and gravity times Z1. So these are all equivalent to each other. So what we could do is, if we knew what P1 was, and we know what Z1 is, or Z1 is, whoops, then we'd calculate at this point a fluid pressure, which is the pressure we would feel if we were inside this can swimming around, or indeed if we were outside it trying to hold it up, the force it applied. So what we can also do, this is also P1 I suppose, right? We could also calculate what happens if we add a second can to this, right? And of course that will have another weight attached to it. And so we can get the weight of the two of them. So weight of 1 plus 2, which is what we'll be holding up if we want to apply P2 here to get this, which would be equal to, well, if you want to do it, unit weight times area, bless you, times Z1 plus Z2. And so this now is Z2 that we're adding. And let's assume that Z1 and Z2 are the same. So in other words, this here is just equal to 2 times Z1, or Z. And we can do the same, that the total weight, it's getting too complicated really, the total weight is equal to these, which we know, and then the total pressure is equal to P1, getting much too complicated for what I'm going to do. The total pressure is going to be the weight 1 plus weight 2 divided by area 1. And so if we do that, we should end up with something which is unit weight times area times Z1 plus Z2 divided by area, knock these out, which is equal to unit weight times 2C1. So the point is that the pressure at this lower point, P2, is going to be given by the location here. And I think you know this, right, for sure. Looks like I can't draw very well. So the pressure here is going to be double this. This has to go through the origin at 0. And so the net effect is that if you look at the slope of this curve, and you take a small portion of it, then this is a change in pressure, small change in pressure dP, that occurs with a small change in distance dz. And you could also write this instead of as being pressure is equal to unit weight times, which is equal to 2 times P1, right? Because this only differs from this one by a factor of 2 in here. So we've doubled the distance, we've doubled the pressure. So we know this has to be a straight line, right, from just the geometry of that. And so we know that the pressure is going to be equal to the unit weight times the elevation change between that. If we want to look at this on a small scale, on a portion of this, we can just look at a small portion of this, just by taking a derivative, and we can rearrange that, if we so wish, as a change in pressure with elevation is equal to unit weight. And so that's only saying that the slope of this curve, dP dz, is constant. It doesn't change shape as you go down. In this particular case, we'll find out that it might change in some cases. But you might also remember that we started off with an expression that said something like dP dz is equal to minus the unit weight. And so the reason for that is merely the fact that we've chosen our coordinate system so that elevation change is positive upwards. And so in this case, we are going down with depth. if it's in a swimming pool, you expect as you go down in depth, you increase in pressure. So this pressure, as you go deeper, the pressure increases, but as you go deeper, the z elevation decreases, right? You're going down, you're going in the negative z direction. So merely to make this a positive coefficient as a function of this coordinate, choice of coordinate directions, we choose a minus sign there. No reason other than that. And so we've basically been able to identify for ourselves how pressure would change with depth. So if you sit at the surface and you go down some depth, if we know the rate at which pressure changes and we know how deep we go, we can just integrate that to be able to figure out exactly how the pressure might change with depth. And so to cut a long story short, we can calculate the pressure at depth. How? Well, we can just take this expression. We can write it the way that we had it before. dP is equal to minus unit weight times dz. We integrate it from a place where we have relative to the pressure and depth. Sorry, this is positive z up here. And if you choose a point, actually it's exactly the same figure that we have. This is P1. This is P2. This is Z1. And this is Z2. So in other words, if we know the pressure here and we want to calculate the pressure at this point, which we don't know, then we just need to know how far separated we are from those. So certainly for a incompressible fluid, of which most liquids are incompressible fluids, beer, wine, of course, which are mainly water anyway, right? Water is basically an incompressible fluid. Surprisingly, if you look at the modulus of water, the bulk modulus we talked about, it's roughly of the order of 2 gigapascals. If you look at the modulus of rock that you'd see as you come up the Mount Nittany Expressway, that maybe is 10 or 20 gigapascals. So only a factor of 10 or 5 times stiffer, if you like. But for an incompressible fluid, the key issue is that density is not a function of pressure. It doesn't change with pressure. Air does, because it's so compressible. And so what we can do is we can integrate this. I lost my train of thought, didn't I? And so we can integrate this from point 1 to point 2. And we can integrate this from location 1 to location 2. And if we do that integral, we end up with what? P2 minus P1. I'm just doing the integral and substituting the limits. Is equal to minus, can't lose that, elevation, and the difference in elevation between the two locations. And so, in other words, if we wanted to figure out what pressure 2 is, we can just write that as pressure 2 is equal to plus P1, take that to the other side, minus the unit weight of Z2 minus C1. And that gives us the pressure at point 1. We just have to be careful in this that we honor our sign convention. And honoring our sign convention means that this is a negative number, this is a more negative number. Or this could be a positive number, and this would be a smaller number than that in a negative sense, right? And so the other way that you might end up wanting to write this is to think of this height here as equal to h. Don't know why this... okay, didn't want to do that, did I? And if that's the case, then you can also write this as the pressure at point 2 is equal to the pressure at point 1 plus the unit weight times the height. Because Z2 minus C1, Z2 is more negative than Z1, so this will be a negative number, It's a negative of a negative number, so this would be a positive number. So this is true in all cases. This is how you might want to write it. We're thinking of going down in depth, which we often think of. You know, I do the same thing. So you go down a swimming pool, you know that pressure increases, and so that if you start off with P1, for instance, being on the surface, then this is equal to atmospheric pressure, which is, we can take a 0 if we're doing it in terms of gauge pressures, and then you can get the swimming pool pressure just as equal to the unit weight of the fluid. Unit weight of water is what? 10 kilonewtons cubic meter. So 100 kilograms per cubic meter times gravity, 9.81. So it's really 9.81 kilonewtons per meter cubed, and you can get the pressure at any particular depth. Okay, so that's one way of doing it. So that's the poor person's way of being able to figure this out. So pretty straightforward. Stacking cans on top of each other. Differential calculus is really just that. You have lots of different little cans. They happen to be of height dz, and when you stack them all up and do something with them, you end up with being able to calculate what the integrated fluid pressure is at depth by integrating between two limits. That's really all we're doing. So calculus, you know, this is the first year, maybe, hopefully, that you see some utility in some of the things that you've done for the first 2 years of your university career. You know, chem, physics, math, all seem somewhat esoteric, but it ultimately all fits into something, hopefully, that's somewhat useful. Okay? So incompressible fluid and the fluid pressures that are related to that is an important concept for us. So let's also do something else. So we've made the point, perhaps you've made the point again today, that in looking at all these cans of liquid, we've made the point that there's only one important rule that we need to know about coming into this class. What's the law that we need to know? F equals ma. Newton's second law, right? So this could be our can of water, have another can of water, have another can of water, etc. Think of a ball. It could also just be water that's floating around. So the fundamental constraint that we have to put on this, everything we do, is that force equals mass times acceleration applies to this. So the other thing that we could do, which we'll do now, by the way, if you look in your notes, you'll see that we've just gone through about 4 pages of derivations in 1 page. That's kind of the mantra for this course. Is that we like to look at, for instance, if you have that can of water, or the water you have in your backpack, and you go up in an elevator, what's the pressure that you'd feel if you were swimming around in that? If you fill the elevator up with water, and the elevator goes up to the 100th floor, do you feel a higher pressure or a lower pressure in that water? If you're sitting at the bottom. What do you think? If you're going up, would it be higher or lower? I think it's higher, right? And the way I'd rationalize that is that if I'm going up in an elevator, my knees creak because obviously it's trying to accelerate me against my own inertia, my own substantial inertia, and my knees creak. And so that would be the same kind of response. The water on the bottom of it would feel on the bottom of the container. So the container is having to push up against it, so the container must be feeling heavier. And it's feeling heavier because it's accelerating it up. So it would increase if you go up, and conversely, well, you'd know, right? If you drop down and free fall in an elevator, not an experience any of us would like to experience, I don't think, then the water that you have and the blood inside you become weightless because you're falling at the speed of gravity. And so, and of course, you all know that Otis elevators, that's where they got their big break. Their big break was when a B-24 bomber or something flew into the Empire State Building or the Chrysler Building in New York City, severed the cables on the elevator, and that Otis has this automatic brake system that allows the cable car, the elevator, to actually brake, self-brake, even if it's been sheared at the top. And so that's why if you go into elevators today, you see Otis. They're a long surviving company. But we digress. So let's talk about accelerating fluids. And so we're talking about fluid statics in this part, but so it seems anomalous that we're talking about accelerating fluids. But the acceleration means that the container that's enclosing this, which could be a fuel tank on a car or the fuel in the wings of an airplane, is accelerating. The fluid actually isn't circulating inside that, but it's actually being driven by the acceleration. And so let's be a bit more scientific about what we're doing, and we'll come back. And again, remember that when we talk about derivatives, we're talking about nothing any different from the stacked containers that we've already talked about. This is our right-handed coordinate system. And instead of taking a nice cylindrical container that we had before, we're going to take a nice differential cube. No different, just happens to be square rather than a cylinder. And what we can think of is that acting on the bottom of this cube is a pressure. Acting on the top of this cube is a pressure plus some change in pressure that we don't yet know. What else? We think that this cube would have some kind of weight attached to it. We think that we could be accelerating this cube. And a positive acceleration, of course, is in the positive z direction. So AZ is positive upwards. And what else? And I guess the other thing that we might have is that we might have a height of this, which before we called Z1. But now let's call it dz. Let's call the area of this area, just like we did before. And let's also multiply this by 1. But instead of multiplying it by 1, we'll multiply it by dz, which is still 1, right? If you divide a number or a coefficient by itself, it becomes 1. So the pressure at the top is a pressure plus a small increment. We multiply that increment by 1, so it looks like a differential. The pressure at the bottom is a smaller amount. And so what do we want to do? We want to use our favorite expression from Isaac. I underline these because, of course, the forces are, if we write out this in longhand, it's force in the x direction, force in the y direction, force in the z direction is equal to the mass of this little cube multiplied by its accelerations, right? Because these are tensorial quantities. They have both magnitude and direction. An acceleration has both a magnitude and a direction, as indeed a force does. And so what we'll do is we'll start off with in the z direction, which is the direction we'll resolve in z. Then we can just write the top part of this as equal to this part here, right? So force in the z direction is equal to mass times acceleration in the z direction. No underbar in this case because it's just a scalar relationship. This still has a direction attached to it, but now it's just given by a plus minus, which can be either in the positive z direction, which is upwards, or the negative z direction, which is downwards. Okay? All right. So let's resolve forces. And so what do we want to do? So we have pressure acting on the bottom times an area, right? This is a force. We have a pressure on the top, which we can write as it acts on an area and the pressure plus a change in pressure, which is just this way of writing dp times 1, which we chose to write like this. Right? It's negative because it's acting downwards. It's acting in the opposite direction to the positive z direction, which is up. We have a weight. The weight is acting downwards. So the weight would be equal to what? It's a volume, which is equal to area times dz. Right? This is just the volume of that. And if you want the weight of that, we have to multiply it by unit weight, for which we'll use the density of the fluid that's making up this cube times g. Right? So this is, again, a force. And what else we got? So we've taken care of this. We've taken care of this. We've taken care of this. We haven't taken care of this. This is this part here, which is equal to the mass. The mass is going to be equal to the volume, which is the area times dz. And it's going to be equal to the mass times the density. So this again is volume, this is density, and it's going to be the acceleration. And you see immediately we got some things that we can get rid of, right? This and this we cancel. We have lots of A's in there, but let's not worry about those for now. What else could we do with all of this? We have, okay. So we have this here. We have this which is equal to volume. For instance, what we could do is we could divide everything through by volume. So we could divide everything through by area times dz. Divide through by area times dz. And we divide through by area times dz. And if we do that, then what we've taken care of is we end up with an expression which is minus dp dz. Minus, we've got rid of this, and this, whoops, minus g is equal to rho az. And so what we might want to do is we could write that in a slightly different way as we use in the notes for what you have. And so let's do that not just for in the z direction, just rewrite that as in the z direction. It's going to be equal to the minus change in the fluid pressure with elevation minus density times gravity. Gravity acts upwards or downwards, however you want to think of it, minus density, sorry, let me write that differently. I'm just going to subtract this off as a negative sign, and if that's the case, then this is minus density times acceleration in the z direction equals 0. And so you'll see that there's something here that looks kind of like something we've seen already, right? This term here, if you want to think about it, is just equal to the unit weight of the fluid. So dp dz is equal to minus, so it's exactly this expression here. So in the case where we don't have any accelerations, not surprisingly, a static fluid, we come back to be able to represent the behavior that we have, as we said before, which is dp, I'll write as a partial, it could be an ordinary differential, dp dz is equal to minus unit weight of water. But what we can also do with this is we can also do the resolved forces in the other directions. And if we do that, we can do it in the y direction. And we won't go through another cube, but we'll just do it by inference. If we look at resolving it in the y direction, we'd imagine that we have a pressure on this on this face here, which is equal to P. We'd have another pressure on the back face here, which would be equal to P plus dP. And so that's the same as it was before. We would have an acceleration now, which would be in the y direction. So that's kind of the same as it was before. The only thing that is different is that the weight only acts vertically downwards. So there is no component of weight in the y direction, which is horizontal. And so take it on trust, but you could imagine that the expression that we'd get from this just by doing that, you can look at your notes if you really feel that you need to get it, would be the change in pressure in the y direction now, minus the component which is due to self-weight, right? This is the weight. And actually, let me also do this. This is a bracket, if I can draw it. This bracket here relates to the forces. This bracket here relates to inertia. So it's just F equals ma, written in a different way. And so if there's no weight that's acting in the y direction because it's horizontal, the weight is acting vertically downwards, there's no component horizontally, so this term has to be 0, and this term has to be the density multiplied by the acceleration in the y direction, which be the same as me taking this ball and just moving across the room with it, right? I'm accelerating as I go across the room. And so that is a fluid that instead of being in an elevator, it's on the moving walkway at the airport, per se. And likewise, the x direction is in the horizontal direction, and it's equal to, by inference, in the x direction, it's equal to the change in pressure as you go in the x direction. There's no component of weight, and if you apply an acceleration in the x direction, then this equals this. And so those are the basic equations that we'll deal with for a motion of a fluid. We can write them in compact form. The reason for writing them this way, I guess it's a bit rude of me to do that, wasn't it? Some of you are writing, I know. The reason for us to write it in this way is that we can actually write them in compact form. And if we write them in compact form, as you'll see in the notes, let me just do it. How do we do that? It's something like, typically we'll write them the other way around. We did the z direction first because it's the most difficult one, because it has the self-weight of the fluid that is acting down. But typically we'll write this as pressure just in compact notation. You'll see it in your book also. Actually, let me not write the P here, write the P on this side. Minus this, minus unit weight 0, 0, minus density multiplied by AX, acceleration X, acceleration in Y, and acceleration in Z. So that's the other compact way of remembering it, if you think in those terms. And so those are the equations of pressure change, if you like, in a static fluid which is accelerating. It's not oxymoronic. It's a static fluid that's accelerating because the fluid in the container is not circulating, but it's physically just being translated either vertically, in which case the acceleration with AZ will be either positive or negative as you go down, or horizontally as you go in X or Y directions. The other important thing to note is that this only comes, we'll do some examples with this. This will only come into play if it's an acceleration, right? So the pressure change, if I grab one of your bottles, the pressure change that occurs as I do this only occurs as I take it from 0 meters a second to 2 meters a second. It only occurs when it's accelerating. If once I get it to 2 meters a second and I keep on going, then it doesn't change, the pressure doesn't change, right? It doesn't stay that magnitude. It only occurs when it's constantly accelerating. So it's the same as when you go up in an elevator. You feel your weight acting on your knees when you start up, if you're going up, but then as you reach a steady velocity, then you're just the same weight as you would be if you're not accelerating, because you're not accelerating. Right? So that's the, yeah.
So for this equation, you have the z direction.
Yeah.
Negative dp over dt minus unit weight minus
Yeah, acceleration z.
0. So if dp over dc equals negative unit weight, what that equation becomes is positive unit weight minus unit weight minus rho az equals 0. So don't the unit weights just cancel out? You're just left with negative rho az equals 0.
Az is the acceleration in addition to gravity.
Right.
So you always have gravity acting. And so actually, if you fall, then the pressure is 0, right? So if you're free falling and your acceleration is g, it would be falling with gravity, then the pressure change with depth would be 0. Is that what you're saying?
Specifically for the first two terms, negative dp over dz minus unit weight, don't those cancel out because dp over dz equals negative unit weight.
Acceleration so if you're accelerating downwards, then you would be a negative acceleration. So gravity we take as being 9.81 meters a second down, and it's not included in that. If I was throwing myself down at acceleration due to gravity, then my acceleration would be equal to minus 9.8 meters a second. And so they would cancel out, and that would be weightless. Right? So this is a negative quantity. So this is the unit weight of water, which is about 10 kilonewtons per meter cubed. This would be the density of water, which is 1,000 kilograms per meter cubed, multiplied by minus 9.8 meters per second squared, which would be a positive number. So this number would be positive. It would be equal to this. This and this would cancel out. So the pressure change with elevation would be equal to 0. And so if you're physically throwing yourself down at the same velocity, same acceleration due to gravity, and you look at the pressure distribution in that water, wouldn't be anything, weightless. Okay? I don't know if I answered your question, but. So where are we? That's I should never say we're close to the end. We're never close to the end. So that is a fundamental expression that we'll use. What we will use it. We've kind of gone ahead of ourselves because right now, if you're not so comfortable with this, the only component of this that we will use is that dP, the change in pressure with elevation, is equal to unit weight of the fluid. And so what we did was, so far, we looked at the case where we have the swimming pool question. Let's ignore the accelerations for now. We've done it. We'll come back to it. If you look at pressure change with elevation, oh, don't click those binders, man. We said before that liquids, if this is a liquid, sometimes we use this a little triangle with a couple of bars on it to signify a free surface in a liquid. We know that as we go down in this, then we can think of this as what? This is dz, and this is dp. The other way, actually, you can think about this, I think, which is useful, is that since we have this expression as dp over dz is equal to unit weight over 1, by similar triangles, you can also think of this as dz is equal to 1. And then if that's the case, then this length here would scale with unit weight, just by scaling. So just from similar triangles, if you think of it in this way. Negative in there, of course. It's there. So what we've said that in liquids, this magnitude of unit weight is typically constant. It does compress when we put a pressure on it. So as you go down deeper within this, I'm going to fall off this chair one of these days when I sit on it. And you get a bit of humor out of that. Certainly the pressure here is larger than is here, and therefore, since it's slightly compressible, then the density is going to be larger at depth, and therefore this really isn't going to be quite a straight line, but it's going to be a line that veers from it. And what's it going to be? It's going to be something that's just above it, right? You'd expect it to be like this. So this is the true line, right? As you get deeper, this unit weight will get larger. And so the pressure change with elevation will get larger. But it's so inconsequential that we don't care about it. However, what we'll do next time is that we'll look at the effect as we go above here when this is air versus water. And what we'll see is that instead of going up at the unit weight of air, which is not constant, then this behavior, this is always true at a single point, but if it changes substantially as you go up in elevation from sea level to the top of Everest, then the unit weight of air at the top of Everest will be quite different from what it is at sea level, and therefore you have to account for that in our integration. So that's what we'll do next time.